Okay, week 10. I'm surprised the promise of finding out about the exam didn't attract more people, but there you go. Guess sure they're all going to watch the video. Maybe what I should do is turn off the video just when I get to the exam bit. Torture them all. Alright, so my experience is runs till Thursday week, 8 days time I think. Stops before the exam. The uni's obsessed with numbers of people who respond, so I guess at least you've got to go and respond. The most useful thing you get from those is comments. So if you've got anything interesting to say, stick it in a comment. Alright, marking, blah, blah, blah. Hate that. That's absolutely the worst part of this job is marking. I can tell you. Anyway, we'll sort it all out by the middle of next week, so you'll know where you stand when you come to do the exam, which people seem to be a bit obsessed about. I completely forgot about quiz 5, so I'll put it up tonight and make it due in a week's time. So today I wanted to finish off talking about the concurrency stuff and transactions, and then talk about the exam. Alright, but before that, here's some nerds, a whole bunch of them. And as you might be able to guess from those signs they're holding up, this is people who are at the Postgres conference. Ooh. Can I scroll up far enough? Yes, I can. Alright. So some of the important people. So these are all guys who develop Postgres. It's an open source system. Plenty of people contribute. Someone will come along and write a replication server, and then Tom Lane will check that it's in good stead and then stick it in the main branch, and everyone will get access to it. So, who are these people? Bruce Momjian, he's this guy lurking on the edge here. He wrote a book about Postgres as a database system, using it in a little textbook. It's alright, he goes around and talks about how great Postgres is. Tom Lane is the main developer. He's kind of the Linus of Postgres, so he has the final say on what gets in. That's him there. Josh Burkus, he's one of the other chief developers. I should have checked before I came along. I'm pretty sure that's him. And Gavin Sherry is actually an Aussie who one time when he was in Australia actually gave a lecture in this course. And he is, who do you reckon? Who's the slobbiest looking one? So they're probably an Aussie. Him. So yeah, lots of people who've contributed to Postgres there. I've got one final database nerd. Who is it? That's pretty easy. Bigger question is, where is it? It's close to an airport. Not Sydney. It's in Silicon Valley. It's Uncle Larry's house. It's the Oracle corporate headquarters, which if the resolution was better, you probably could read Oracle up there. I didn't get an invite in, thanks Larry, but I did go and have a look at the outside. So that was not what I call exciting, but it was there and I did it. Alright, let's get on to some stuff. Oh yeah, I wanted to talk about assignment 1 marks. Alright, how do you mark 500 subjective kind of assignment things? Alright, so you all worked in groups. Well, at least some of you worked. Looking at the stats, some people did nothing on the assignment, and they're going to get sprung by what's down the bottom. People who did nothing get nothing. If I saw no evidence of contributing to a discussion, no evidence of editing a wiki, no evidence of even assessing, doing the peer assessment, then you don't get anything. Alright, so how do we do it, or how do we try to do it? And I suspect it's not quite finished. Someone pointed out that they reckon one of the counts was wrong, so I'll have to go and check that, and if I discover some sort of systematic error, I'll fix it and run everything again, which is easy because it's just a bunch of scripts to run. So I ran some queries. The peer assessment system, that's got a Postgres backend. WebCMS has a Postgres backend. So, hey, I can sit there and write SQL queries for fun and collect info about what the ratings were from the peer assessment, what block, well, that sounds a bit political, it's meant to be blog, posts and wiki edits, and stick all this stuff together in ways that I'll describe on the next couple of slides and produce a mark out of 5. Out of 5, I might point out, worth pretty much nothing towards your final mark. So I'm not sure why so much effort was involved. Anyway, so if, I know some of you set up Facebook groups and God knows what else and work there, well that doesn't help because I can't access their databases to do any counts. If there's a whole lot of, if you get a mark, a low mark here because there's no evidence that you did anything in WebCMS, then tell me where there is evidence that you did something, and I'll go and have a look and change the mark accordingly. I think I might rerun those things anyway because I didn't think you could even read that big screen of text, but apparently you can. But I'll try and make it look a bit better. Let's see. Alright, so how do we do it? So peer assessment, that's easy. There's peer assessment database, so I can just run through all of the assessments, find out how many ratings you gave, find out how many comments you wrote. Not many people wrote comments, but it was good that some people did. Compute an average rating. So a lot of this is based on averages because there's big differences between the amount of stuff that happened in individual groups. So someone who did 2 wiki edits in a group that did 100 wiki edits, that's a little bit, but not a lot. Someone who did 2 wiki edits in a group that did 4 wiki edits has made a serious contribution. So it was all based on group averages. So compute the average group rating and the average rating that you got from other people. It's a shame you couldn't give 0, the lowest mark was 1, but I could always adjust by subtracting 1, I guess. And then having got information about you, got information about the average, then work out a mark based on whether you're well below average, whether you're somewhere around the average, or whether you're well above average. And all that really, well, does 2 things. It changes the message, so it might say something like nothing. If you did nothing, it might say you are excellent if you did a whole bunch of stuff well above average, and so on. And also it produces a mark. So all these things I did out of 3, except the wiki stuff was out of 4, I think. Something was out of 4, can't remember now. Maybe it was peer assessment was out of 4. Could have been. In any case, they mapped to a mark out of whatever that component was worth. So for the group discussion, look at the blog, look at the comments attached to the wiki, and work out how many postings you made. Use as a rough estimate of how useful or interesting or significant your posting is, just measure the length of the posting. I assume that since I didn't tell you I was going to do this, that no one scanned it by typing XXXXXXXXX, making a very large posting that said nothing. So I'll assume that's a reasonable measure of what you said. work out the averages for the number of postings and length of postings over the group. And once again, once we've got an average for the group, see how you fit into that. If you're well below the average, then you get a low mark. If you're well above the average, you get a high mark. I'm kind of thinking I may have penalised people who are around the average by not giving them a good enough mark. So I might go back and recalculate everything anyway. And everyone's mark will go up, which I'm sure will make you happy. For the wikis, count the number of wiki edits. This one, interesting. Maybe you allocated someone to do all the wiki editing, which would then penalise everyone else in the group because they didn't. That's something that I could possibly modify the scripts to check. How do you work out whether someone's done an interesting wiki edit? Basically do a similarity measure between the previous version and the version that you submitted, and work out how much you changed as a kind of rough guess as to how much you, how substantive your changes were. And in particular, if I discovered if you changed images, that's probably a big thing to do, so there was a bonus attached to making a change in the image. But largely it was based on the similarity to the previous version. All right, once again, compute averages for each group, and then using your score relative to the average, give you a mark. So I didn't just do this and do nothing, I did do some checking. So I just looked at something that came out of the output and said, all right, let's have a look at this person, see if the counts matched up. All the times I looked, they did. See if the comments they'd made, see if the length measure is a reasonable estimate of substantiveness. And it kind of looked plausible. Whether that's true or not, whether you're all going to say, no, this is rubbish, and if you are, then I'll go through and tweak things a little bit and see what happens. Right, so that's assignment 1. Marking, right, so let's get back to transactions. Right, just a reminder, transaction is a unit of work from the application. So we've got a database system that's backing up an application. A unit of work transfer funds between two accounts. That involves multiple database operations, but conceptually it's a unit. So transactions should behave like they're a unit. So that's what atomic is all about. Either everything that the transaction is supposed to do happens, so we don't just subtract from from the source account, forget to add to the destination account, for example. And that can be particularly problematic. If you start the transaction, you get part way through and the system crashes. So you've done some of the changes that made up the unit, but you haven't done them all. So we either want, so the notion of atomic is that either everything that was supposed to happen for the transaction happens or nothing happens. So if some stuff has happened, that has to be undone, and database systems can do rollback to undo those kind of intermediate changes, if you like. Transactions are consistent. Basically that means that the effect of a transaction takes the database from a state which satisfies all of the constraints to another state that satisfies all the constraints. So that's some kind of notion of correctness on the transaction. We don't want transactions to interfere with each other. Classic example I gave last time, two people trying to book the last seat on an aircraft, and they both arrive at the same time and discover, there's a seat, there's one seat available, I'm going to take that. They both get told, hey, you've booked this seat, but in fact only one of them has been registered in the database as having booked that seat. And durability is all about what happens if there is some kind of system crash partway through, or there's some failure of the storage subsystem or things like that. So Databases are supposed to provide a stable, persistent view of a collection of data. So that's what durability does. Now when we start talking about transactions, we don't normally spell out everything that's going on. The only interesting operations as far as analysing these kind of properties, reading a particular object, which might be a tuple, making changes to a particular object, once again might be a tuple, committing and aborting the transaction. So every transaction is just a sequence of those kind of operations, of course, typically ending with a commit, which we haven't written in any of these examples down, so that's kind of assumed. So when a transaction does a sequence of operations, we can call that a schedule. If we've got multiple transactions running concurrently, the sequence that the operations from the two transactions occur may be interleaved. So we got this example here. So transaction 1 reads X, writes X, reads Y, writes Y. Transaction 2 reads Y, writes Y, and then reads X and apparently does nothing with it. That's fine. And transaction 3 reads X, writes it, and writes Z, which it somehow managed to produce as part of its action. So all this stuff in between these operations, we're assuming there's some kind of computation going on inside the memory based on the information that we managed to get here. So kind of more obvious example is there. So we read in the value X, then we do some calculation based on the value. Maybe we make changes to X and then we write out the new value of X. So here's a sort of arbitrary interleaving of the operations for those two transactions. That's possible, how things might turn out if you're not careful about scheduling the order that individual operations happen. Here's another example, same three transactions, but you can see that the schedule's quite different. All of the operations for T3 happen, then all the operations for T1 happen, then all the operations for T2 happen. Serial execution of transactions is important because we assume each transaction maps the database from a valid state to another valid state, and then starting from this valid state we run another transaction, get another valid state, and so on. So if you do things serially, you're guaranteed not to mess up the database. If you start interleaving the operations in arbitrary ways, it's possible that you can mess up the database. Right, so serial schedules are fine, but not all concurrent schedules are valid. If you've got a concurrent schedule that is equivalent to some serial schedule, then we call that a serializable schedule, and that concurrent schedule is also safe. It's going to produce a valid end state of the database. So this particular schedule here is serializable. And there's two ways that we can characterize serializability. One is by looking at the conflicts between the operations. So an example of a conflict is here. This operation writes X, this writes Y, this operation reads Y. If we did those two things in the other order, if we read Y and then wrote Y, we'd end up with a different result. So we say that those two operations have a conflict. You can't, swap them over. And view serializability is a different way of characterising things that I'll talk about in a minute. So all that's very nice. Obviously it looks good if we've got serializable schedules, because that's going to move us from a database in one consistent state to another consistent state, which is what we want. How do we achieve that? Or what do databases do to achieve that? Well, they use locking and rollback. So basically what locking does is make sure that the read and write operations end up being carried out in a particular order that's going to produce a serializable schedule. Knowing that a schedule is serializable is not a particularly useful thing because the schedule has already run. So all those operations have been done. We assume all the transactions were committed. If the schedule is not serializable, then potentially we've messed up the database already. All the transactions are run, they've finished, and there's been some sort of nasty interaction between them. So it's a bit, analysing serialisability is not something that's useful in practice. Making things serialisable is what's useful, and that's what locking does. Alright, so conflict serialisability was basically the notion that if you've got two operations from different transactions that don't conflict, in other words, maybe they're operating on different objects, things like that, maybe they're two read operations, if you swap the order, it's not going to affect the final outcome of the transactions. So if you can take a concurrent schedule and you can swap non-conflicting operations, and if you do enough swaps, you end up with the schedule that's serial, then we say that the schedule is conflict serializable. So you can either try this swapping idea to see if you can produce a serial schedule, or you can analyse by building a precedence graph, which I looked at last time. And here's an example. So this schedule here is not conflict serializable. I've done as many swaps as I could. So for example, these two operations, I can swap the order that they do. They're both in the same transaction. Okay, that's fine. These two operations, Rx and Ry, I can swap the order of them if I wanted to, because they're operating on different objects, so there's no inherent conflict there. Let me see. That and that could be swapped, so I could do Rx first here and then do Rx and T1 there. That's not a problem. These two operations here, I can't swap them because that's going to produce a different outcome if I swap those two operations, because I'll be dealing with a different value of x. And in fact, there's sort of a long distance problem here as well. This Rx and that Wx in different transactions also conflict. So if I could get those two things next to each other, I still couldn't swap them. So I did a whole lot of swapping and ended up with something like this, which still isn't serial, and I could stand there and swap till I was blue in the face and I'd never end up with a serial schedule, because this is not conflict serializable, and I can determine that by building this precedence graph. So basically what this graph does, we've got a node for each of the transactions, and we put an arc between two nodes, and it's a directed arc or directed edge, depending on if an operation in T1 on a shared variable has to come before a particular operation in T2 on the same shared variable. So let's see, how do we get this arc here? T1 and T2. T1, we do a read x here. T2, we do a write x here. Those two things can't be swapped. So that read of x in T1 has to come before the write of x in T2. So that's where the precedence occurs. So T1 does something before, has to do some particular operation before a related operation happens in T2. And basically you draw down, or you put down all the precedences, and if you end up with a cycle in the graph, then it's not conflict serializable. Basically you can't swap things to ensure that you end up with a serial schedule. Here we could realise that it wasn't serialisable just from those two edges, because that's a cycle, but we can follow cycles all the way around as well. So it's definitely not a serialisable schedule. Right, view serialisability is a different way of looking at serialisability, and basically what it's talking about is who gets to look at a particular version of a particular object. One thing about it is that it's less conservative, which means that something that's view serializable might not be conflict serializable. But the fact that it's serializable at all means that it's a safe schedule. Even if it's not conflict serializable, if it is view serializable, that's okay. So once again, we've got this notion of equivalence. So view equivalence between two schedules tells us whether, let's say this is a concurrent schedule with all the operations interleaved. This is some serial schedule for those two or three transactions. If they're view equivalent, then this concurrent schedule here is safe. And the basic idea is we look across, here I'm just talking about two schedules, but we can have multiple schedules. If our concurrent schedule over here and our serial schedule over here, if they both initially, well, if all of the reads for a particular object are done the same in both schedules. So in this example over here, in fact, I'll go into, it's hard to do it talking about it in the air, and also that they write the same final version of an object. So let's have a look at an example. I haven't got, have I got an example? Oh, I didn't. All right, so here's the definition of view equivalent. So basically, here's our concurrent schedule. Let's say T1 is the transaction that reads X, reads the initial value of X. If it's going to be view equivalent to this serial schedule over here, then in this schedule, T1 also has to read the initial value of X. If they're going to be view equivalent, let's say T2 writes the final value of X over here, then in the serial schedule, T2 also has to write the final value of X. And sort of as we progress through the transactions, let's say in the serial schedule, T2 reads a value of X that's written by T1, then in the concurrent schedule, T2 has to read the value of X that's written by T1. So if all of those conditions hold for all of the shared data items, and if you can find one particular serial schedule for which all those conditions hold, then we say that the two schedules are view equivalent, and therefore the concurrent schedule over here is safe because it's equivalent to a serial execution of the transactions. So as long as you can satisfy those conditions, and it's a little bit tedious to do the calculation, it's okay if you've got two transactions and not too many shared data items. But if you've got 3 transactions or 4 transactions or 10 transactions all running concurrently, then it's a matter of finding one of the serial schedules for those transactions that's view equivalent. And there's no way that you get, well, you can kind of narrow it down a little bit. If you look for, if you look at the concurrent schedule and you see, aha, X was read by T1 as the first transaction that read X. So I've got to look at a serial schedule that T1 reads the value of X first. So I can limit myself to just those serial schedules, but then I've got to do this equivalence check on the serial schedule. And if it's not equivalent to that serial schedule, then I've got to find another serial schedule where T1 reads X first, then do this check. If they happen to turn out view equivalent, then fine, this schedule's safe. If they're not, then I've got to look at another serial schedule and another serial schedule and just keep looking until I find one that satisfies this property. And if I look at all of the serial schedules and none of them are view equivalent to the concurrent schedule, then the concurrent schedule is not view equivalent and therefore not safe. So you could reduce this n factorial to something a little bit less based on what I said before. If concurrent schedule reads X in T1 first, then you've got to choose a serial schedule over here that does the same thing, and then look at all of the other shared data items. Right, so that's two different ways of looking at serializability. The basic idea is if you've got a schedule, and if it turns out to be equivalent to some serial schedule, either conflict equivalent or view equivalent, then we say it's a safe, you've ended up with a safe result. The real question is, how did I end up with that schedule that's equivalent to a serial schedule? Certainly serializability tests are no use, because as I said, you've already done the transactions and messed up the database if they're not view or serial conflict equivalent. And in any case, it's expensive, as we saw on the previous slide, to do view equivalence testing. Maybe drawing a precedence graph is a little bit simpler. But in any case, like I said, they're done after the event. So what we need is some way, or some operations that can be applied in each individual transaction, and if those operations are inserted into the transaction, then when we execute the transactions, we end up with a schedule coming out of it that is equivalent to some serial schedule. And there are a number of ways of doing this. Standard kind of approach is to use locks. You can use version-based scheduling, which doesn't really do scheduling at all, but just make sure that one particular transaction isn't looking at the wrong version of a variable, of a shared object. So that's kind of useful. Timestamp-based transactions, so you look at all the transactions that are waiting to run, you look at the operations, and you order the operations according to how long it's going to take each one to run, to make sure that the operations occur in a serializable order. And the final one is you forget about trying to control the system, you just run it, and once you reach the end, so this is almost like the serializability check, but once you reach a certain point in the transaction, typically when a transaction reaches the commit point, you check that maybe nothing's gone wrong. Well, that, in fact, you're not checking maybe, you're checking there haven't been any conflicts, is essentially what you're checking. And if there haven't been any conflicts, then you can commit. If there have, then you've got to roll back that transaction and try again. Right, so I'll have a look at lock-based and multi-version concurrency control. Right, so here we got standard locking operations, shared and exclusive locks. If you want to read something, you apply for a shared lock, so someone else who wants to read the same object can do so. But if you want to write something, you've got to get an exclusive lock and make sure you're not writing and someone else isn't writing at the same time. If you try to get a shared lock and someone else has already got an exclusive lock, then you get blocked. So the whole idea of the locking is that if you try to acquire a lock, if you can't acquire the lock, then that transaction just stops for the time being, and hopefully eventually that lock will be released and then you can continue. And for exclusive locks, if there's any kind of lock on the object, so if someone's already read it and you decide you want to write it, then you can't continue. And if someone's said, I'm going to write on this, and then you come along and say, I'm going to write on this, you don't get to go. So even if you apply those rules, so if you stick locks in the appropriate place, every time you want to read an object, you apply for a shared lock. Before you write it, you apply for an exclusive lock. And if you do all of that, you can still end up with non-serializable schedules. But if you acquire the locks in a certain way, and basically what a transaction has to do it has to acquire all of its locks before it does any unlocking. So if it can acquire all the locks that it needs, then it's probably got, you know, exclusive access to whatever objects it's going to manipulate. It can do all of its manipulations. Maybe it's already done some of them earlier, and then it can unlock. So if all of the transactions are structured or behave in that way, then we're guaranteed serializability. So you've got to acquire all the locks you need, then you can do whatever you like, and then you start unlocking everything. Now, of course, if you think about it, doing things that way, acquiring all the locks, doing stuff and then writing out, and anyone else who's trying to acquire some of those locks may be blocked. So it's, to some extent, and this is really what lock-based concurrency control is all about anyway. It's trying to enforce things to be more serial than they would otherwise be. Now, there are other problems with locking, of course. Deadlock. If you ask for an exclusive lock on X, this guy asks for an exclusive lock on Y, and then you progress a bit further, those two lock operations are going to be blocked. Then you ask for an exclusive lock on Y, and then he asks for an exclusive lock on X. Then you're both blocked, waiting on each other to release the lock. And of course, since you're both blocked, no one's ever going to release the lock, so you're stuck. Starvation is all about when a transaction does get blocked, it has to wait somewhere for the lock that's been blocked on to be unlocked. And if there are multiple transactions waiting on a particular lock to be unlocked, then you've got to choose one of them. And if you always end up not choosing a particular transaction, then that transaction, or we say that transaction starves. Okay, so it's stuck there waiting for an unlock. Before it gets a chance to continue, someone else comes along and tries to acquire a lock, the same lock that the starving transaction is waiting for. When that lock gets released, the new transaction grabs it and continues on, and our original transaction is stuck there waiting to continue and can't. So locking involves introducing some new operations, an exclusive lock or a shared lock. Here I've been a little bit preemptive, so I've applied an exclusive lock because I know eventually I'm going to write this object. In theory, I could do a shared lock here and then upgrade that to an exclusive lock here before I did the write. But okay, T1 says I want to access object X, apply for an exclusive lock. Okay, no one else has, so off you go. And T2 says I want to get an exclusive lock on Y. It's a different object, so there's going to be no blocking that happens. So this sort of arbitrary interleaving of operations can certainly happen in that context. And we know there's not going to be a problem because there's no shared objects. In Schedule 2 there is a shared object, so T1 acquires an exclusive lock on the object, then T2 tries to acquire an exclusive lock on the object. Since it's already been locked, it has to wait, so these dots represent T2 waiting, and T2 is not going to go until T1 unlocks X. So it can do all of its stuff to X and then unlock, and then T2 continues. And of course, looking at this, you can see that what locking has done, it's forced serial execution of the two transactions. So we're guaranteed to be serializable. We don't necessarily end up with a completely serial execution, but what we will end up with, we're likely to end up with more serial looking execution if we use two-phase locking, but we can end up with some safe concurrency going on, like in the first example. So what locking does, typically it makes less concurrency, and the whole point of concurrency, of course, was that we could do multiple things at the same time and get better throughput in the system. So locking reduces the capability of doing that. But the thing that it buys us, two-phase locking especially, is that we know that the transactions aren't going to interfere with each other and produce an inconsistent database. So a couple of other things about locking. Reducing concurrency lowers throughput. There's also how fine-grained do you lock. I've got this shared object X. I haven't said what X is. I haven't been very specific. I did suggest that maybe it could be a tuple, maybe it could be a whole table. So I want to do something to a table. I want to give everyone a pay rise, lock the whole table, do an update over all of the tuples in the table, give them a pay rise, and then release the table. So if I do that, everyone else is blocked from that table while I'm doing the update. Not necessarily a good thing, especially if the other transaction is just reading the table and it doesn't particularly care whether it gets the old salary or the new increased salary. So in theory, it's better to lock small items like tuples. So if I lock one particular tuple in the table, then I can access all the other tuples in the table. Locking a small item means that I'm likely to do a very quick update if I'm just playing around with a single tuple. Therefore, the lock gets released quickly, which is always a good thing. On the other hand, locks don't come for free. You've got to have a lock manager in the DBMS. So if you've got more locks on small objects, that's more overhead in the locking system. So databases will typically allow you to do things like that. Databases will introduce locking automatically for you, but you can also do, you can explicitly lock things if you want, if you don't think the database is going to do the right thing. Right, so another approach to concurrency control sounds really horrible at first sight. It sounds like it's going to be so inefficient. Maintain multiple versions of the database, and every time a transaction comes along, it looks at a particular version of the database that's appropriate for it. You don't actually have to have multiple versions of the entire database, but what you do have to do is keep multiple versions of individual tuples. And what happens then is that a transaction that comes along has to look at an appropriate version of a tuple. And basically what that means is a version of the tuple that existed when that transaction started. It's possible that that tuple's been updated by another transaction, but we don't see that. We just see the original version, which clearly means there's got to be two versions of the tuple sitting in the database. So MVCC and locking means that if you acquire an exclusive lock to do writing, an exclusive lock, then you don't block other people that want to read. So you can go and fiddle and create a new version of the tuple. Everyone else can come along and read the old version of the tuple. And reading doesn't block writing. So if someone's reading, that's fine. They see the version of the tuple that existed when the database, when the transaction started. If someone else comes along and wants to make changes, that's fine, because this transaction is still going to see the correct version of the tuple. So this is quite a nice idea. In fact, Postgres was the first DBMS that actually did this, and Oracle and plenty of others have copied this strategy. So how does Postgres actually implement multi-version concurrency control? It doesn't make a complete copy of the database all the time. What it does is tag each tuple with the transaction that created it. And if we know the transaction, we know the creation time. The other thing it does is that it links a tuple to the next version of the tuple. So that if you want to, you can go forward in time and find the most appropriate version of the tuple. So you've got multiple versions of tuples persisting in the database. Now, there's a cost to this. Every time the database wants to look at a table, it should only see the tuples that existed when the transaction that's doing the reading started. There may be lots of versions of tuples sitting in the table that are newer, and you've got to have some way of ignoring them. And the only way you can do that is basically to say every time you grab a tuple from a table, you check which version it is or check when it was created, and doing that you can check whether the tuple should be visible to you. But that's an overhead that you have to put up with on every access to a tuple. You might say, that sounds pretty bad. And if you go and look at the Postgres source code, the actual code for checking whether the version of the tuple is visible to you is actually quite long, but I think it's relatively efficient. The other issue that you think, if you think about multi-version concurrency control, is you've got multiple versions of the tuples. Do those old versions persist forever? No, they don't. They only exist until their deletion time. So when you got an old version of a tuple, it's basically either deleted or it's been superseded. So it's going to have an end time, if you like. If all of the transactions in the system started after that end time, none of them can see that tuple. So basically, the tuple is like garbage in a memory allocator system. So it's a tuple that's sitting there, no one's ever going to be able to see it. What do we do with it? Well, there's a process called vacuum that runs through the whole database, looks for tuples that are basically out of date, and then gets rid of them. So you can see there's time overheads because you've got to do a check on every tuple, and there's space because you're storing multiple versions of a tuple, but it turns out it's worth doing because it reduces locking. Therefore, you can increase the concurrency in the system. Alright, so transactions, you can be explicit about them. You can say you want to begin a transaction, you can say that you want to end a transaction with commit, and you can even explicitly say, I've reached a certain point and I've discovered there's an error, so I want to abandon this transaction altogether. You can use rollback to do that. Sometimes rollback will be kind of forced on you. In the case of optimistic concurrency control, if you reach a point, you try to commit and you discover, oops, there's been a potential conflict between me and another transaction, then you'll be forced to roll back. Other ways, other things that can cause rollback, if you do a raise exception during the execution of a function and that function's embedded in the transaction, it'll roll back the transaction. And with triggers, if you return a null value from a before trigger, basically saying, I don't want to make this whatever change activated this trigger, so roll back that change. You can apply different granularities of locking. You can lock tables, you can lock tuples or rows. In Postgres, a lot of the commands that you'd execute that make changes to metadata, for example, incorporate their own locking mechanisms. So something like alter table, you want to make sure no one else is messing with the table while you're getting rid of a column, for example. So you have to exclusively lock the entire table. And if you're doing update and delete, certainly you've got to apply a lock to the row that's being changed. You don't want someone else to be changing it at the same time. Even though with multi-version concurrency control, that's not really an issue. You just make new versions of the tuple. A lot of SQL, and here I'm talking generally about SQL-based databases, a lot of them will simply, you don't have to explicitly unlock anything, and especially with two-phase locking, there's a notion that you ask for a whole lot of locks at the start, and when you're finished, you unlock everything. So a lot of SQL-based databases will just do an unlock at the end of the transaction. So you don't explicitly have to say that's what you want to do. Oh, I jumped ahead of myself. Alright, so that'll do for concurrency and transactions. Let's have a break and then I'll talk about the exam.